Let's take a look at the solutions to derivative bootcamp day 2 handout. And the first question, we are looking at a total revenue function. So here's revenue, cost function. Here's the cost function. Don't forget the plus 900, both in thousands of dollars. You're looking for the rate at which the profit is changing. They don't give you profit, so you got to create that profit function because we want P prime. So profit is revenue and cost, revenue minus cost, how much you get minus how much you have to spend. And you're just substituting those values in, revenue and cost. Use parentheses here for the cost because with that you need to have that negative sign distributed out to this guy. You might forget that. So distribute the negative, so he's negative. Now we need P prime, so we take the derivative. We're using the extended power rule and the chain rule. The 1/2 comes down, keep what's inside, subtract 1 from the exponent, chain rule out what's inside. The negative 2200 comes along for the ride. Extended power rule and chain rule. Bring the 1/3 down. Keep what's inside. Subtract 1 from the exponent. Chain rule out the derivative of what's inside. And that's it. You're done. You're just looking the rate at which they're not asking for it to occur at a certain value of X. Let's look at number 2. For this guy, you have a demand function and a price function. Demand is a function of the price. Price is a function of the time in days. They want demand as a function of time. So you need to take this function and substitute it in here for the P. You do that. This is the notation you use, and you get this guy. You can go ahead and rewrite it as a fraction so that when you take the derivative, you can use the power rule, but you don't have to. Sorry, that got cut off with the copy. So we're going to take the derivative, bring the negative down to get negative 90,000. Keep what's inside. Subtract 1 from the exponent. Keep it. Subtract 1. Chain rule out. 1.5 is the derivative of what's inside. You can rewrite it or you can leave it like it is. We're looking for the rate of change of the quantity at t equals 90 days. So d prime of 90, we substitute 90 in for t. Or if you rewrite it, the 90 goes down in here. And when you do that, and I see this should be 90 here. When you do that, you get 292 units. Remember, it's the rate of change of quantity. That's why it's units, and it's per day at 90 days. We did a couple extensive examples of position, velocity, and acceleration. When you're given a position function, velocity is the derivative of that, and acceleration is derivative of that one. No units are given here, and so we can just leave it at, for this guy, each of these functions. Find the velocity and acceleration at t equals 4. So you just substitute the 4 into each of those. For velocity is 45, and acceleration is a constant 10. And I would say you could add to this, since there's no units, it's units per, and yeah, I would just say per hour. You'll always be given units. I have no idea why they're not on here. So something else to make a note of is that there are questions at the beginning of each of these sections. You really should work with your study group and try to answer those questions that are at the beginning of each one. Page 2, we have number 4, you're dropping an object. So you're using gravity, distance from where you're dropping it. So we're going to use velocity and acceleration. Here is the position function. It's in meters, so be aware of that. Take the first derivative, take the second derivative. They want to know the velocity and acceleration of the stone at 3 seconds. So find v of 3 and a of 3. When you have that, you do need to write your solution because they're asking for velocity and acceleration, not this notation, although you have to use the notation to find the solution. So at 3 sections, the stone, or it, is dropping at 29.43 meters per second, and it's accelerating at 9.81 meters per second squared. For the next one, the position in meters of a rock in free fall, and it's the same kind of question. Here's the distance formula. They're asking for the rate of change of the position That means we just need the derivative of that position function. So you take this guy and take his derivative. And then what's the rate of change? The rate of change, the position is changing as a rate of 13.34 meters per second with that t sitting there. So that's unusual, right? But it depends on what the time is, how fast that its position is changing. So here you have a function for that rate of change, not just a number. And that's okay. Just be aware, sometimes it's a number, sometimes it's a function. Now we have a view of distance in miles is given by this guy with a root. Rewrite that, 1.22h to the 1/2. Find the rate of change of that function, rate of change derivative. And so you've got that. How far can one see to the horizon from an airplane window at a height of this? And so we just find from the original function, put your number in, and you can see 122 miles. Now they're asking for the rate of change, so that's the derivative of v. And when you find that derivative, substitute the 10,000 in. And the view is changing at 0.0061 miles for each additional foot at 10,000 feet. And that's because this is given in feet. Now explain the meaning of part A and C is that the rate at which the view is changing or increasing given h feet. So be careful with this one. Really weird, right? That there's a v and we're using this idea of position, velocity, acceleration, and this v. So this is just checking, can you use the notation where v is not v for velocity, v is the name of the function. And so it's a little different than usual in notation, but if you just stay true to the derivative and each level you're doing, you'll be fine. For the next one, the position of the particle moving along the coordinate line is given by this, s in meters, t in seconds. So the whole thing is in meters, and you're being given some time in seconds. Find the rate of change of the position at t seconds. So the rate of change is the derivative. We want to evaluate the derivative of 5 seconds. Take your derivative, substitute the 5 in. Here you go. That's what we need. Here's the function. Here's its derivative. Here's its evaluated at 5. You get this. Don't forget to write your solution. Position is increasing at 1/18 of a meter per second after 5 seconds. And then the last thing we have, last thing is population. And so the initial size is 800,000 here. P is the population given by this function. T is in years. Find the growth rate. So dp dt, that's taking the derivative of p with respect to t. Remember, we use this notation because we're about to go to variable functions with multiple variables. When you take this guy's derivative, this guy, derivative is 0. This guy, bring the 2 down, 8,000 t. Find the population after 20 years. That's population, not change in population. So just p of 20. And you end up with that many people. Find the growth rate at t equals 20. Now you take that derivative evaluated at 20, substitute it in, you get this, and here's your solution. So I would just say, remember, everything you see on here has lots of notation in it, where Sam's going over your supplemental problems, and you have some issues with those. And most of it is because of units being missing and this notation. Notation, notation, notation. We keep preaching that. You get docked for points for it. What I highly recommend is when you're doing your online homework and any kind of practice whatsoever, you write the notation down. Don't be lazy when you do that homework. Actually write the solutions down and use notation when you do it. So that's it. I hope you have a great day.